Okay. Take roll. Oops, I need new paper. All right. Let's see. Jonathan. Nope. Don't need that. Caitlin. Brian. Not here. Kendrick. Not here. Jose. Nope. Miguel, you're here. Gabriel. Nope. And Tracy is here. Okay. So, last time we were talking about standard deviation. And standard deviation is a measure of location. So, when we calculate standard deviation, of course we have two formulas for it. We can have a population, which is lowercase sigma, and that is the sum of all x values minus the mean, mu, in this case, squared over n. And then we also have, for a sample, s equals almost the same thing. The sum of x minus x bar squared over n minus 1. Okay? So, just to quickly go back over this, what we do to calculate our standard deviation is we first find our mean, whether it be mu or x bar. Again, that's just if we are doing a population, we'll call our mean mu. If we're doing a sample, we'll call our mean x bar. And once we do that, we subtract x minus the mean, square it, add all those up, divide by either n or n minus 1, and then take the square root. And that will give us a number. And that number represents a distance. Okay, so it's a distance from the mean. So if you want to go one standard deviation from the mean, it's just take whatever number this is, go that many steps from the mean. So maybe we get a standard deviation of 2. So to go one standard deviation from the mean, we would go 2 steps, since our standard deviation is 2. Okay, so here's an interesting question for y'all. Can we ever have a negative standard deviation? Say no, Miguel? Okay. Does everybody agree with that? Tracy, agree? Okay, good. Absolutely, you cannot have a negative standard deviation. And here's why. Think about it. Sure, when we subtract x minus mu, or x minus x bar, if x is below that mean, then when we subtract that number, we're going to get a negative. Sure. However, when we go to the next part, which is squaring all of those new values, if, say, we got a value of negative 2, when we go to square it, negative 2 squared, that's negative 2 times negative 2. Negative times a negative is a positive. So anything that might be negative in here to start with suddenly becomes positive when we square it. And then all we're doing from there is adding, then dividing, then taking a square root. So there's really nothing else to make a negative there. So standard deviations are always positive. Okay? Any questions? Okay, so they are always positive, and that makes sense because, again, what I said was a standard deviation is a distance. It's a certain amount of distance from the mean. And distances cannot be negative. After all, think about it. If I were to say, well, the distance from this wall to that wall is negative 10 feet. Does that make any kind of sense at all? No. There's no such thing as negative 10 feet. Distances cannot be negative. Okay, so once again, standard deviation is a type of distance, and thus it cannot be negative. So today what I want to do is look at some more types of distances, measuring how our data is packed, basically. So what are the distances between specific points of data? How is it distributed? Okay? So another way that we can look at distances, so compare basically all the points of data to each other, is with percents. So if I have a set of data, let's say 6, 13, 22, 5, 17, 18, 21, 2, 1, 4, 15, 2, 16, and 14. Yeah, I can find standard deviation. I can find a lot of things about this. But for this particular example, what I want to do is I want to find what's called a 5-number summary. And a 5-number summary is a way of finding some values to compare the distances between our data points. And it's actually quite simple. In fact, we've done most of this already before. We just didn't realize we were doing it. So, first thing we want to do to this data is put it in order. It's always a good idea to put our data in a ranked order. So let's see, 1, 2, 2, 3, 4, 5, 6, 13, 14, 15, 16, 17, 18, 21, and 22. Okay, so we've got all of our data ranked in order. So again, one way that we can do this is by finding a 5-number summary. And a 5-number summary basically says we can split any set of data into quarters. So split it into 4 parts, basically. Well, just like if we were to divide, I don't know, like this ruler into quarters. First, we'd start by cutting it in half, so right there at 6 inches. Then we could further subdivide each of these halves into another half. And if we wanted to, we could go further than that, another half and another half and another half. For right now, though, we're just going to separate this data into half and then half again for each side. So basically split into 4 parts, or quarters. So the first thing to split this in half is to find the median. Of course, the median is the middle number. So if we find that median, we will have the halfway point of our data. Okay, so let's take a look and see where our median falls. So count in from each side, looking for that median. We get 13. So 13 is the middle of our data. And again, what we've just done now is we've split our data into 2 halves. We've got a half over here, we've got a half over here. So we can do that again with each half. So looking at this half of the data, where's our median? What's the middle number of this half? 3. Okay, do that same thing for the other side of our data. 17. So what we can say now is if we read our data, by the time we get to the point 3, this is 25%. So we've gotten to 25% of our data by the time we get to 3. This is called our first quartile, or Q1. If we keep reading our data, by the time we get to 13, we have seen 50% of our data. This is known as the second quartile, or Q2. And of course, we also know that this is the median of our data. We keep reading. By the time we get to 17, we've seen 75% of our data. This is our third quartile, or Q3. Okay, but I said 5-number summary. So we've got 3 of them. Where's the other 2? Well, to finish up our 5-number summary, we also need our minimum and maximum. Because the minimum and the maximum will give us the actual range of our data. Okay, so we know where our quartiles are. We know where the start of our data is. We know where the end of our data is. So to make this a little bit more easy to read, we will graph it. Okay, so let me just make a number line real quick to graph this on. Okay, so I've got a number line here that goes from 0 to 25. And so what we want to do is we want to plot all of our 5 numbers in our 5-number summary into our number line. So, starting with 1, here's 1. Keep going. Our next number is 3, so 3 is right there. Next one is 13. It's right there. Then next one is 17. .22 is right here. Okay, so to complete this graph, what we're going to do is we're going to box in our quartiles. So our first, second, and third quartile, right here, here, and here, are going to get boxed in. Okay, so this box again represents the first quartile to the second quartile to the third quartile. Then from these quartiles, we will measure to the minimum and the maximum. And we now have our graph. This graph is called a box and whisker plot. Here's the box, here's the whiskers. So what this does for us is show us graphically what these numbers represent. Because again, percents in this case are distances. So to get from here to here, to get from here to this one is a 25%, there's a certain distance. To get from here to here, there's another certain distance. And we can now see those distances on this graph. Now you can imagine that if we had the numbers 1 to 22, and we had every single number, you know, we're not skipping from 6 to 13. We have 6, 7, 8, 9, 10, 11, 12, then 13. And we don't repeat any numbers, so we just have 1 to 22. All of these distances would be exactly the same. Okay? So we wouldn't have lopsidedness like we do here and here. So what this does for us is it allows us to see, again, visually, where this data is in relationship to the other data points. How is it spread out? What are the distances between our quartiles? And so we can see here in this case, from our first quartile to our second quartile, so from 25 to 50%, there's a very large distance. We're jumping a pretty big gap to get to that 50%. To 75, it's not a very big jump. So our data is not evenly dispersed, and we can see that how it's actually dispersed in this box and whisker plot. Any questions? No? Makes sense? Okay, let's try another one for practice. So I've got the points, let's see. Eight, 7, 12, 12, 7, 13, 6, and 5. Okay, so again, what we want to do is we want to split this data up into 4 parts and then make a box and whisker out of it. So we're going to need to order the data. So y'all do me a favor. What's the first point? What comes first when you order this? 5. Keep going for me. What comes next?
2.
Keep going.
7, 8, 12, 12, 13.
Very good. All right, so we've got our data ordered. And again, we want to split this up into 4 parts. So what do we need to find first to split it into half? The median. Yeah, perfect. So if we look at our numbers here and start counting in, we get 2 numbers in our median, 7 and 8. So what does that mean our median actually is? So it's halfway between 7 and 8. 7.5. So our median is 7.5. Okay? So now, we want to do the same thing for each side of data. So what's the median on this side? 6.5. Okay, and this side. What's our median? Yeah, it's still 12. Think about it. If we have 2 numbers, one on each side of the median, but they're the same, so 12 and 12 in this case. 12 plus 12 is 24. Divide by 2, you get 12. So yeah. So we've got our first quartile, second quartile, and third quartile. What else do we need? Minimum, maximum. Perfect. So here's our minimum, here's our maximum, and I believe we now have all 5 of our numbers for our summary. So now we are going to need to graph this. So I'll come up with a number line real quick for us. Okay, so this one goes from 0 to 15. Plenty of space for our box and whisker plot. Alright, so let's start plotting numbers. First number, 5. 1, 2, 3, 4, 5 is right there. Next we have 6.5, which will be right here. Next is 7.5. So 6, 6.5, 7, 7.5 is right here. Next is 12. 9, 10, 11, 12 is right there. And then 13 is right next to it. So again, we want to start by making a box around our quartiles. So here's our first quartile, our second quartile, and our third quartile. Draw a box around them. And then we want to draw from the edges of our quartile range to the whiskers. Okay. So this one's almost got the opposite thing going on. From our 25% to 50% range, pretty tiny. There's a much larger distance between our 50% and 75% range. But again, this allows us to see visually how our data is distributed. Again, in a normal set of numbers, if I just had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way over to 13, all of these would be equal distances, or equidistant. There wouldn't be these lopsided things. It'd all be the same distance. But because we know that data does not follow that kind of trend, or at least not usually, we need to be able to understand how our data is actually arranged in relationship to other data points. And so that's why we have these box and whisker plots. Any questions? Okay, good. Now the box and whisker plot only gives us the 25, 50, and 75% locations. I'm out of paper. So what if we want to know some more specific locations? Well, we might want to calculate the position of specific percents. Maybe instead of going for 25, we go for like a 30% or a 80% or something like that. Something that's not listed on our quartiles. Okay? So I've got another set of data here. 49, 59, 60, 67, 69, 72, 75, 81, 86, 88, and 93. Okay? So, lucky for us, this data has already been ordered. We don't need to worry about ranking it ourselves. But instead of finding those quartiles and finding a 5-number summary, we want to find a little bit more specific percents. Okay? So, it's actually pretty easy to do that. We're going to need two numbers. We will need n and we will need k. So n, we already know that. What is n? What is the definition of n? Yeah, yeah. So it's the number of data points we have in a set. So for this one, how many data points do we have? We have 11, yeah. So our n is 11. Now k is something we haven't seen yet. When we choose our percent, so let's choose a percent real quick, we'll say 30. Or how about 53? Okay? When we choose a percent, k is going to be that percent as a decimal. That's really important. It has to be as a decimal. Essentially what we're saying here is that 53% is out of 100. But we don't have 100 data points, we have 11. So we want to equate this percent, instead of being out of 100, to be out of 11. Does that make sense? Okay. So the first thing we need to do is to change this from a percent to a decimal. And the way you do that is to divide by 100, or move that decimal to the right, to the left twice. So this would be 0.53 as a decimal. And now it's just a matter of multiplying k times n. That's it. This will give us what's called an index. The index is the amount of steps you need to take through your data set to get to whatever percent we just calculated. Okay, so let's figure out what our index is here. So k times n, so that's 0.53 times 11. Let's see, 0.53 times 11. We get 5.83 for our answer. However, that is not how we want our answer. We want our answer as a whole number because, again, these are steps that we're taking. And we want to take whole number steps. We don't want to have to go, piece by piece with these decimals. So what we'll do is we will round this. It'll either round up to the nearest whole number or down to the nearest whole number. So what is this rounded to the nearest whole number? Is what? 6, yeah. So our index is 6. And again, what that means is that this is how many steps we need to take to get to the point that is 53%. So, if we take 6 steps, it's 1, 2, 3, 4, 5, 6 steps. And this point represents that we have reached 53% by this time. Now, is 72 the exact location of 53% of our data? No. If we wanted to put this on a number line like we did with our quartiles, 53% would be somewhere between 69 and 72. But what this is telling us is that by the time we've gotten to 72 in our data, we've reached at least 53%. We've passed 53% by this point. Okay? Any questions? So, I'm guessing high school wasn't that long ago for y'all. It's a nightmare amount of time for me. When y'all were seniors, you probably got a score where your school told you you're in a certain percentile of your class, right? So what they did there is they took everybody in your graduating class and calculated your GPA. And those were the data points. Okay? Then what they did is they found the percentiles. So they found the, 50%. They found the lower 10%. They found the upper 10%. So maybe they found the 90 and they said, okay, past 90 is 10%. That's how they figured out where you were in relationship to your rest of your class. And that's what we're doing here. We're figuring out where this is in relationship to the rest of all the other data points. That's what this percent is doing. And again, this is as a distance. This index is a distance. Okay? Any questions? Let's do this one more time, one more practice of this. So let's actually use some data we've already seen. 5, 6, 7, 7, 8, 12, 12, 13. Okay? So once again, we want to find a particular position in this data. Let's say we want to find 80%. Okay? So again, we need to know two numbers, n and k. So what is my n for this data set? 8. We have 8 data points, so our n is 8. How about k? What is our k going to be? 0.80, or we could just say 0.8. Okay? So what do we do with n and k? Multiply them. So 8 times 0.8 is going to give us 6.4. So our index will be this number rounded. So again, we're rounding to a nearest whole number, so it's 6. So we count 1, 2, 3, 4, 5, 6. So by the time we reach this point, we've gotten to 80% of our data, which means that above this is the rest of the 20%. So 12 and 13, these two data points are in the upper 20%. And then all of these numbers are in the lower 80%. Does that make sense? Okay. Cool. So again, we can get some rough ideas about where our data lies in relationship to the rest of our data by getting a 5-number summary and plotting it. However, if we want to know more specific positions for our data, so like where does this particular number fall, where it falls in the lower 80%. Okay, in fact, we can do this the opposite way around. We can calculate from a position and go to the percent that it is. Okay? You just follow this backwards. Any questions? Okay. So, remember that Friday we will have a quiz. And that quiz is going to be a lot of the same stuff we saw last week, because I want to make sure that we have that stuff down. So that stuff is mean, median mode, weighted mean, okay? And then we're also going to add in standard deviation and the box and whisker plot. So know how to find a 5-number summary, and I'll probably give you these two formulas. I'm not going to tell you which one represents which. Remember that this is a population and this one is a sample. So I'll give you a problem that says, you know, this is a data set collected from a sample, and you need to be able to choose which one of these would be correct. Okay? So, I think that'll do it for today. I'll see you all on Friday, and I hope you have a good one.